Okay, welcome everyone. It's my pleasure to announce Professor Roger Blandford for today's colloquium. Roger did his PhD in Cambridge under Martin Rees, and he shared an office with our own Peter Martin here in the audience. A little bit later, he became a professor at Caltech, after which he moved to Stanford, where he still is today. And we had the pleasure of having the vice or the deputy director of SEECS. And today we have actually the director of SEECS, the Simon's collaboration of extreme electrodynamics of compact sources. So today Roger is going to talk about M87 and his ideas about that. And well, Roger, thank you very much for joining us. Go ahead.
Well, thank you very much, Bart, and thank you everybody else for the kind invitation to return to Toronto. I've, of course, been here several times, but not for several years, so it's really nice to be back, not the least to meet with my SEECS colleagues, Chris and Bart Peder and Gibwa and others, and it's good to see that. In fact, the very first talk I gave in the continental United States was at Peter Martin's invitation to come here. I think in must have been 1974. Sorry? No. Oh, yes, of course, yes. Yes, no comment. But I think you can guess what I might have said. Okay, all right. He came here, and in fact, it's a sort of reversion because the topic I talked about was something that this is about, which is the jets that come out of active galactic nuclei. And at that time, Martin Rees and I had written a paper called the twin exhaust model of double radio sources, and so this is the return to that. And my wife Liz and I came up here, and we had a wonderful time. But on the way here, we drove for the first trip in a car that we bought from a plasma physicist. And so it was a great big Mercury Montego, 3 times the volume of the one we'd left behind in England. And we drove here. We got as far as Rochester, to the glorious fall colors, and then the exhaust fell off. This was an omen. But at any rate, we had a great time, and it's lovely to come back here again. And this is one of the reasons why I chose to talk about this topic. I think there are other things I should say. The title may seem a little inscrutable, and if there's any representatives of Rice Krispies here who are going to have me for project infringement, I would point out that snap, crackle, and pop are the words that some engineers, and indeed cosmologists, curiously enough, use to describe the 4th, 5th, and 6th derivatives after velocity, acceleration, and jerk. They call them snap, crackle, and pop. Look it up. Why they would do this is quite beyond me. But at any rate, I will use these words later. But what I really want to talk about is M87 and what might be going on there. And I would say that my collaborators on my sort of current forays into this business are here. People I've talked with over the years, and in some sense they contributed to much of the story I'm going to tell you, are there. All should be thanked, and none should be blamed. So this is SEECS, as mentioned. This is Kaipak, where I work, and this is where you work. Okay, all right, so let's go back. Whoops. There we go. Okay, so for those who haven't just awoken from a coma, the EHT collaboration made an image of a black hole, or the shadow of a black hole, as they called it, in the nearby galaxy M87, and this great big orange ring here. This was a tremendous piece of work. The way it was done was using very long baseline interferometry, using separate telescopes scattered around the globe, as you can see here. And basically, if you imagine just two of these telescopes, say between Greenland, as it now is called, and SMA, and which is in, excuse me, that's in Hawaii, for example, or actually the one that's most important is down in Chile, but to apex down there. So let's take that long baseline there. Just take two of them. Basically, what it does is you take the amplitude of the radio emission from a distant source, and at two telescopes, you cross-correlate it, and that tells you a component of the Fourier transform of the brightness distribution of the radio sources you're looking at. So it's just a Fourier it's a machine for doing a Fourier transform. Now, that makes it sound awfully simple. It's extraordinarily hard. This technique was developed by pioneers at meter wavelengths in the 1960s. It's now done at millimeter wavelengths. That's extraordinary. And the technical accomplishment to make this happen it requires making all of the telescopes work together. That's very hard. They're all different, so they've got to be made together. It requires getting all the different agencies in different countries to work together. That's even harder. And hardest of all is to get the astronomers to work together. But they all did it, and they all pulled it off, and they made these glorious images by looking at the sky in this way, making a Fourier transform map. And I'll come back to that again. So the first image that was published looks like this, and and you see it's sort of bright at the bottom, and it's a sort of ring, and that is the black hole shadow there. This is essentially the resolution, the full width half maximum of the image made using this technique. They can, and so you can see it's not terribly well resolved. I'll come back to that point, but it's resolved well enough to see the shadow. And there are plans for going to space and so on, which will improve this a little bit, not a lot. Using more sophisticated and with some rather large priors and machine learning, which solves all problems, you can make a slightly higher resolution image. And polarization, of course, has been measured here. Many other sources have been measured. It's variable and so on. I'm not going to review the observations. I just want you to get what you already know, that there is there's an image seen here. We know quite a lot about it, and we're going to learn more, because although these images have been made at 1.3 millimeters, they're already getting interference fringes at 0.8 millimeters. That means it's lambda over b. That means better resolution. That's coming. M87 is the first of the extragalactic sources to show a jet. It was discovered in Lick Observatory in 1918 by Heber Curtis, and we now know a lot about it. It's imaged on different scales by radio telescopes, and these are techniques which, as I say, would that's rather kind of spoil something. Okay, never mind. Okay, so what I want you to notice here is, as you go from larger and larger scales, you see a jet that's coming out, and the key thing I'll mention is what we've discovered is that most of the emission in these supposed so-called jets, these outflowing relativistic plasma, comes from the walls of the jet, and so we'll come back to that again, but that's just the observation. And if I then, let me go on. So if I make when I first officially saw the image of this, I sent it to my collaborator, who's a collaborator on the present work, Naomi Gobus, and 20 minutes later she said, no, it's all fake. That's what it is. So somewhat more slowly, I also hark back to my youth, and so this is what I thought it was. But eventually we were persuaded that radio astronomers were not pulling a joke. They'd really made an observation, and it's great. And it, of course, inspired the SEEKS icon we have down there. Okay, so let me say a little bit about black holes. And I suspect this is superfluous, but I'll say it just in case not. I won't, like Larkin's poem, they were sort of born in 1963, and the two things happened at the first Texas Symposium on relativistic astrophysics, and one was a announcement by Roy Kerr that he had found a solution to Einstein's equations. Here he is, which showed seemed to describe a space-time that was spinning. It could be associated with a black hole, and it was a truly remarkable discovery. And we now know that that space-time is not just one example out of several. It essentially is all you need for astrophysical black holes. And here I do not concern myself with the febrile imaginations of theoretical physics who've taken these sort of ideas into much different directions, and they have used this as a sort of touchstone for investigating many issues in both quantum and classical mechanics, and that's great. For humble astrophysicists, all you need is a Kerr space-time, which has mass, of course, which is just the scale, and spin, or equivalently an angular velocity. That's all it is. It has an event horizon. Moviegoers know about that, although not necessarily the complete details. And it has around it an ergosphere, which is a region, a spinning black hole. It has a region around it where an observer, for example, on a time like geodesic, must orbit with respect to a distant frame of matter. And there are various, there were a huge amount that was discovered in about 7 or 8, in about 10 years, about a decade after the announcement of the Kerr metric. Its properties were elucidated by many people, and just to call out two that were important here. One is Roger Penrose, and I'll come back to this, pointed out that there were negative energy orbits, total energy orbits within the ergosphere, which meant that you could, with suitable engineering, put a particle onto one of these orbits, which meant it was going backwards into the black hole, and you could extract, that means you could extract the energy from the spin of the black hole, just like a spinning top. You could extract energy from it by this thought experiment of putting a particle into a negative energy orbit. The other one was the area theorem that was demonstrated by Stephen Hawking. And this was that the area of the black hole had to increase even though its mass could decrease by extracting energy from it. And that puts a limit on the amount of mass you could get out, or energy you could get out of a spinning black hole. And it works out to be just less than 30% in a maximal way. And in practice, about 15% of the rest mass of a black hole is there for the taking as spin energy. That's the sort of practical limit. And so this in 1963 set the stage, if you like, for grand astrophysical drama. And then at the same meeting, and almost a disjoint audience, Martin Schmidt announced the discovery of quasars, which the first and prime example was called 3C273. And I'll just point out for the astrologically inclined that M87 is 3C274 and quite close in the sky. But these quasars were brighter than 1,000 galaxies, the brightest of them. And we now know that they have massive black holes in their galactic nuclei. They can be active, as in the quasars themselves, or dormant, like the one in our galaxy, which is only 4 million solar masses and pathetic. But don't be ashamed of it, because you wouldn't want to live next to a quasar. And of course, we now know of black holes that are stellar-sized, and perhaps some that are intermediate-sized, and in the, again, the febrile imaginations of theoretical physicists and astrophysicists, primordial black holes of very small mass, which might be evaporating by Hawking radiation, for which there is no observational evidence, but maybe one day. Okay, so that's more or less it. So now I want to talk about what might be happening physically in M87. And what I'm going to do here is present what I oversimplify as the sort of standard model. And then I'm going to present an alternative. not so much in the spirit of these guys don't know what they're talking about and it's all wrong, etc., listen to me, but more in the spirit of presenting an alternative, which I think has the merit of being refutable, a sort of quality that is not so common in contemporary astrophysics, where things tend to be able to survive. And so I'm going to try and explain those statements. So let me first explain the standard model, and in some sense I have some association with it. It's basically, the idea is we've got a black hole here, and that black hole has gas that swirls around it. And the gas that swirls around it is thought to form a disk. And in this sort of standard model, which I'm oversimplifying and generalizing and so on, is forms a very thick, what we used to call an accretion torus. I mean, we worked in this in the 80s. My colleagues and I and many other people worked before, in fact, before and many afterwards. And the idea is you make these sort of funnels here, and those funnels are the channels in which these outflowing jets are expelled. So that provides a channel for the outflowing jets. And if we look on the larger scale, then this is a simulation done 16 or 17 years ago. And we've obviously many more simulations since then. A feature of this model at that time, which I'll say a bit more about, was that magnetic field lines are held in place by this orbiting torus of gas here, and some of them thread the horizon of a spinning black hole, and that extract those magnetic field lines, unlike Penrose's rock thrown backwards into the horizon from the ergosphere. Those magnetic field lines extract energy from the spinning black hole and send it up the jet in this direction. And this torus here has to be supported by the pressure of hot ions with temperatures of about 10 to the 12th degrees, and the electrons have to be significantly cooler with temperatures about 10 to the 11 degrees or so, again in round numbers. And this is the story, and it's one that I'm going to present an alternative to. There have been many more simulations since then. The power of these simulations is extraordinary, looked at in many different ways. I will not do justice to them. Sometimes there's an acronym that has been introduced into this business calling these magnetically arrested accretion disks, or MAD disks. So MAD is what they're supposed to be, and that's kind of caught on, so I'll use that phrase. And this is the alternative. And one feature of these models, these MAD models, is that the magnetic field is what I would call on the weak side, in round numbers, about 10 Gauss, or I should say 1 millitesla. Sorry, 1 millitesla. I don't know whether this is an SI school shop or a CGS school, but okay, whichever you prefer. I'm bilingual. Okay, but it's low field. But anyway, so what we have then is thick iron pressure supported tori collimate the jet. So it's like a pea shooter and sends it out. Okay. Now, before I present an alternative, let me just give you some numbers. So the mass is measured by various means, a little bit controversial, about 6 billion solar masses. That's the mass of the black hole in M87. And that mass provides a unit of length and time. In length, about 10 to the 10 kilometers. In time, about 8 hours. So 10 to the 10 kilometers is the size of the outer solar system. All right, it's the size of the outer solar system, 10 to 10 kilometers. And 8 hours is about the duration of this talk. So, and what this means is the orbit of gas, say, in the middle of this torus would be about a month, using Kepler's laws, essentially. Okay, it has spin, and I'm going to treat the spin essentially, it's an unknown. I'm just going to guess it. In what follows, I'm going to guess it, but just to give the general idea, and I'm going to say it's about 0.9 of the maximum it can be. There's a maximum to how fast a black hole can spin, and it's about 90% of what it should be. It's about 60% of its maximal angular velocity. It's an equivalent statement. And the other thing that's important, and I don't know whether there's a stick. This will work. This is the prop I think I need. So if I imagine that this here is the black hole, then let's take Chris as the observer. I mean, he'd like this role. And then we have the jet, and the jet is defined by the angular momentum of the spin of the hole. It's presumed to align with the spin of the hole. Then it's like that. So the angular momentum points into the sky away from us. That's the orientation we have, and that's consistent with what we know about gas swirling around it and what we see in the observations. So that, but it's at a fairly small angle, and this angle is defined is measured by radio astronomers. It's not a secure number, and it could in principle be wrong, but it's the best we have, and that's 163 degrees. So we're looking more or less along the counter jet when we look at this thing. So that's kind of important for what follows. Okay, let's keep on going. The amount of spin energy you've got is enormous. It's good for 1 trillion years. And now, important thing here, if you ask the radio astronomers, and by extension myself, because I follow what they do, what the power in the jets is, it's about 610 to the 36 watts. It's 2 orders of magnitude, or 2 or 3 orders of magnitude more than the power that you measure from the gas swirling around and what the people in M87s, people in the Event Horizon Telescope collaboration see, and so on and so forth. So most of the power that we've evidence for is in the jets. Okay? And it could be that, you know, it's in a low state or whatever now, but this is the sort of simple way to look at this. And the mass supply rate is, again, that's measured by other means, again, not totally secure, is quite high relative to what is presumed in the models that I'm going to present an alternative to, of 10 to the 22 kilograms a second or so. This is not high by what you might expect for gas falling into the cluster, but this is what's measured. Now, let me just say one more thing is there's this I remember I said this is the highest resolution non-EHT observations. You can see here a sort of wall. This wall is either something like a shear layer, a boundary layer, for those who know about fluid mechanics, or it is a current sheet for those who know about electromagnetism. There's a current sheet there between and a jump in the magnetic field, and it's almost certainly both, and that's what we see. And we call that generically a sheath. That's the word for it. So I'll use that word again. Okay, so here are some numbers. And let's I just emphasize that, you know, they're still a bit quite soft, these numbers, but they're going to get better. Okay, so what motivated my colleagues and I to think about this was essentially 4 questions. Why are the disks and the plunge so dim compared with the power that's made in the jets? That's the first question. The second is, if the gas flowing into the black hole, as measured at least by the models, is orders of magnitude smaller than the gas that's supplied at large radius, how is it driven away? What's the source of the power that drives it away? Because you've got something with 0 energy, it falls into a potential well, and then you've got to give it positive energy. You need a source of power. Okay, the third one is these jets, as you may have observed, and I will tell you, are collimated. They're being continually focused. 10,000 gravitational radii, 10,000 black hole radii away from the source. Something has got to be squeezing them in. And the fourth is one that's been known about since the 60s. These powerful jets are associated with what's called elliptical galaxies, which are quasi-spherical things, rather than the spiral galaxies like our own. So those are 4 questions. And this motivated us to consider models with the field being much larger. And the reason for this is, of course, then the field is quite strong and can power the jets at the level at which they are seen. So that's 10 millitesla, but it has other implications, which is where I'm headed. So the only way you get any respect in this business is not by having physics ideas, but by having an acronym. So we've tried several. MAD work very well. So we'll try HEMD, which is whole energized magnetically mediated ejection disk. And so what we said basically was that instead of the whole thing that you're looking at being powered by gravitational energy, with gas spiraling inward in the disk, releasing its energy and producing photons and so on, instead of that, it is essentially all powered by the spin of the black hole. It's a little bit like the sun, which in the 19th century was well known to be powered by gravitational energy and would live for 10 million years. And then it was found to live for 10 billion years. And so we had to invent nuclear physics to solve our embarrassment. And that worked out well. So, this case, it's the spin of the hole that's providing almost all of the power for the whole operation in a source like this. And so the field is much stronger. The jets are more powerful. They are essentially electromagnetic structures. And the contention is that about 10% of the jet power gets applied to a disk of gas that is orbiting it. This is on the largest scale. On the largest scale, there's a disk of gas here. And that disk of gas is a sort of reservoir where gas flows in, and then instead of accreting onto the black hole, is blown away by power extracted from the spinning black hole. And it's blown away in a organized hydromagnetic wind that goes out. It's over scales of up to 1 million times the size of the black hole. That outflowing gas contains magnetic field lines. And I'm not sure how much MHD people here know, but the key thing about magnetic fields is that there are two sort of pop psychological things that happen when magnetic fields meet conducting plasma. One is called go with the flow. That is, magnetic field lines move with the gas if they're with conducting plasma. And the other is push-pull. This is pop psychology, and push-pull means it's got magnetic field lines, has a pressure in all directions, but in addition, a tension like a pulled elastic band. So it's got a tension as well. And these magnetic field lines in this wind produce magnetic field that spins around it with a hoop there of magnetic stress. That hoop of magnetic stress constricts the outflow and causes the collimation of the outflowing jets. And that's the contention, and that's the way of solving these problems I just mentioned on the very largest scale. It really matters what the outer boundary conditions are, and that's really the gas that's flowing in from large latitude, as you see in elliptical galaxies and not in spiral galaxies. So that's a feature of this. But I'm going to concentrate now on the inner edge, on the inner part here. And here we've got to communicate some of the spin energy of the black hole, not just to the jet, but also to the disk. And there are two generic mechanisms that could be responsible for doing this. One is little loops of magnetic field attached to the spinning disk will also penetrate. Those magnetic field lines will penetrate the horizon, and the more rapidly spinning black hole will just like a sort of provide like a capstan, will provide energy and angular momentum going out to the disk. The other is there is magnetic field lines that go between the hole and the disk. Those magnetic field lines are, it turns out, unstable. And those magnetic field lines can also, through the instabilities, transport energy outwards radially as well as up along the jets. So this is the sort of general story that I've just outlined here. And this is a rather different view. The disk is relatively thin. We call it an ejection disk rather than an accretion disk because essentially all of the gas in it is ejected rather than accreted. Two Latin words, but very different meanings. two Latin roots, I should say, in very different meanings. Okay. Gosh, I'm running out of time, seriously. Okay, all right. So this is what's going on here. So this is a slide I was going to show to try and explain in terms of elementary electromagnetism how energy is extracted from the spinning black hole by having magnetic field lines thread the surface like this. I clearly don't have time to do that, so I will leave that here, but if it comes up in a question, I'm quite happy to give this sort of quick explanation. And so basically what happens is the magnetic field lines, just like you might do with a spinning top, take energy out of the spin of the hole, put it into the jet, and as I now say, perhaps 10% of that goes into the disk to drive away all the gas. Okay. Now, what we're doing in this study, and this is sort of developed from the picture I've just given you, is trying to set up a different way of thinking about the M87 observations. And instead of doing what is useful and the common, there must be many hundreds of papers already in this style, you do a simulation, you forward model, and then you describe the observations. This is the approach that's used. It's good, it has some value, but the fundamental physics that underlies those simulations is very uncertain, let's put it like that. We've got relativistic plasma moving at transrelativistic speeds, and we really don't understand how it behaves empirically. So what we have instead is trying to work backwards, as I sort of illustrated, I hope, from the observations. And instead of saying, we have a model, and in some cases there are 100,000 of these models to be compared with observations, instead say, let's just try and guess the most likely places you could be looking at around a black hole. So one of these places is the sheath, where there's a shear layer and a current sheet. That's likely to be highly dissipative. You expect that to be a source of emission, and you see it to be a source of emission. Another is the gas. There will be some gas and some magnetic field flowing equatorially into the black hole. That's another prominent source. A third prominent source is the jets themselves. Simple solutions are stationary and axisymmetric and totally invisible. However, that's highly unlikely to be the case. This is likely to be unstable as anything. There's 10 to the 19 volts of potential difference across here. It takes 10 to the 6 volts to make an electron-positron pair. Go figure. It's going to be highly sparky. It's going to have sparks all over the place. That would be my guess. I can't model it. I can't defend that statement, but that would be my guess. And so my guess is this jet in this region here is going to be very, very sparky. And I'll come back to that point and its significance. I'll not make any more of this statement except to say there are different versions of what happens to the magnetic field lines near the equatorial plane, which is likely to be a prime place of emission. One is that the field lines get dragged into the hole as this version, or as we say, they go vertically through. Again, I won't explain why, but can bring that, if any brings it up in questions, I will do so. So I recently reread, for reasons I can't imagine, the Divine Comedy, and it occurred to me the 9 circles of hell actually do have a physical interpretation, not in the order in which Dante provided them, but they do have an interpretation here. Lust is fatal attraction. Black holes are hungry and they desperately want to be fed, and they're not being fed very much at the moment. There's fraud and there's treachery. I won't go into this. This limbo is where the sparks may be and so on, and wrath is what happens in the things. And so anyway, this is not serious. Okay, all right. Now I come to my title. I've got this far. Okay, snap. This is the first of the 3 words. What is different, qualitatively different, about the high field models that I have been advancing rather than the low field models is that the cooling times of the emitting electrons are short. They're very short compared with the other time scales you have. And so what that means is that if you make an electron to emit at a wavelength of 1.3 millimeters, it will lose its energy on timescales which could be as short as minutes and are going to be certainly shorter than many hours. So that makes them short compared with the orbiting times and so on. So looked at this way, an alternative limit to looking at some sort of smoothly varying emitting volume is instead to see the emission as being characterized by a whole series of flares, impulsive flares that happen one after the other. It's a limiting case, if you like, and obviously it's going to be a bit of both, but in this case we're saying it's much more of this than the other. And so there's going to be emission from local fast flares. Now, what would cause these flares? Well, of course, it's magnetic field. If you think about magnetic fields of the sort that are observed on the surface of the sun in magnetic flux tubes and so on, there's a process which Sasha Filipov may have actually mentioned when he came here. It's called magnetic reconnection, in particular relativistic reconnection. And this is likely to be a very good accelerator of particles. A less well-studied process that I think could actually be even better is what I call magnetic luminescence, which is instead of making a tangle and then having magnetic field lines essentially exchange particles on some resistive time scale, to make slip knots, which will naturally form with these flux tubes. And those flip knots will resolve themselves at the speed of light in a relativistic environment. And that can also be a strong accelerator. So the magnetic field line, if you like, is snapping. That's the source of emission, the snapping magnetic field. And the timescales, as I say, are short. And you might be looking in some models, say tens or hundreds of flares at any one time. And these might be observable. This is the thing we're going to be looking for, is the consequence of having these flares rather than strong things. So, let's just move on to the next one. So this local acceleration is very much a feature of the physics that we think is going on here. This is where the particle acceleration ought to be in those insights that I just gave you. So I'm going to have to finish very soon. This is not good, but nevertheless, I'll do my best I can. So the next part was Crackle, and these are the flares. And the flares themselves, if you just think about a simple version of a single flare, that flare will be time asymmetric. So a single flare will not be up and down each time. It'll have a fast rise and a slow decay typically. Actually, it'll be the other way around. It depends. It can be the other way around. But the key thing is it'll be asymmetric, and this can be sought by just taking the existing data of the total flux that's measured and looking for the arrow of time, which requires a 3-point time correlation function, or a 2-point time frequency cross correlation. Both of those should exhibit this rather strongly if there are flares going on. This is Crackle. Those who know about the history of radio will know that in the First World War, radio operators heard lots of crackle, obviously, in their earphones, and they also heard what we call whistlers. This was falling in frequency, and that's a different reason from this, but this is the same thing you're looking for here with the monitored data. Now it's going to be at 2 frequencies. Okay, so you're going to seek an existing data. Now, the next thing is that I'm going to not be able to have time to go through this, but would love to go through it because this is what I've been quite exercised about in the last week or so, is how to actually trace the rays through the Kerr space-time. Here we've got the Kerr space-time. This is just the metric written in a simplified form with none of the terms defined. There's a Boyle-Lindquist coordinate here system. So there's time, which is time as measured at infinity. There's radius, which is well defined, and 2 angles. These are the 4 coordinates you typically use. And we can trace rays from a source to the observer. Lots of rays, this is just an example here. And it's very straightforward exercise. Many people have done it. It was done in the 1960s, first of all. But there's one sort of key thing that makes this sort of different from a general space-time is that there are constants of the motion along these rays. There's an energy, which is obvious because it's stationary. There's an angular momentum, which is obvious because it's actually symmetric. But there is also a third one, which is a hidden symmetry, which is called the Carter constant. And so there are three constants of the motion. And that means tracing the rays is a straightforward, simple exercise of solving first-order differential equations. I can do it using Mathematica on my laptop as fast as I need for anything I do. But there's another way of looking at this, which I will not say about, but in fact, I think it's actually much more powerful and instructive. And that is, instead of using the rays, using the wavefronts. I'll say no more about that unless anybody brings it up. But I think this is A, far more instructive, and B, if you want to do big investigations, it's much faster. But anyway, I will say no more about that. Okay, so this seems not to be, oh, there it is. Okay, so let's continue with Crackle. If we follow this optics, every source in the universe is imaged by every black hole in the universe an infinite number of times. That's not terribly helpful. All we're really interested in is where there's a significant number of photons that we can see. And basically what happens is there are basically two, a typical suit can have up to two rays that connect the source point with the observer in the places of interest to us, the areas of interest. And what can happen is that those rays can be tangent to a caustic surface. So if you imagine using Chris as the observer and this is the black hole and it was not a spinning black hole, then there would be essentially a line focus behind. But if I was spinning, then that line focus unfolds into an asteroid shape. It's small, but it's still bigger than the solar system, bigger than the Earth's orbit. So it's as big as an astronomical unit. And that is, I will come to in a moment, but the two rays that we see from a typical source point close to that caustic, fairly close to that caustic, not very close, are going to be highly magnified, and one's going to come after the other. So if there's a source there, we'll see an echo. Okay, and if the first thing does that, the next thing will do exactly the same thing, but later. That's what we're looking for. It's like microlensing. For those who know about microlensing, it's like that. Okay, and so going back to the orientation that I advertised, this is the sheath here. So if you like the jet and so on, and the rays, you might be looking at the sheath, you might be looking at the jet. Moving on. Okay, these caustics. So this is what the caustic looks like. I had an excellent student, Kevin Rausch, very much in contact with, and his thesis was on essentially plotting out the caustics in a Kerr space-time, and this is highly relevant here. And this is what I said the caustic surface looks like. And if we imagine a source coming across, sorry. Oh, that's right. Okay, thank you. Good. Your optics. Thank you. Okay. Black hole. Okay, all right. Then we might see something interesting. This is the magnification here. It can typically be up to thousands, the magnification when you're close to one of these small caustics. And so kind of understand that. There'll be occasional little sparks. You'll see them, and you can look for them. So this is, if you like, the pop, the caustic crossings. So if we imagine close to this caustic, we'll have the traditional two rays, which will be typical. And if we imagine a source crossing the caustic like that, it will make a feature in the flux that looks like this. It's very distinctive and very predictive. And this 4, you might think that's not much of a magnification. That's logarithmic. Okay, so this is so you could look a point source would look very bright, and so you'll go from 2 images to 4 images to 2 images. And what happens if we remember when I said about the interferometer, we've got all these telescopes all around the world. Each pair of telescopes will see 2 images, 4 images, circling the black hole on the sky, going right round on what's called the Einstein ring. They'll go right round like that. That will be a very distinctive image, a very distinctive signal in the visibility as measured as raw data by the interferometer, not after lots of image processing. So in the raw data, it should be there. And I'll just say parenthetically that you're actually in the regime here where diffraction and plasma's effects can be relevant, but I will say no more about that. So all I've said here is applicable to other sources, which I will not have time to discuss. And so at this point, I probably had better just finish with my summary. The EHT observations are a magnificent accomplishment. There's this MAD model, which is a thick torus supported by hot ions, which may well turn out to be right. It has a weak field and quasi-steady emission. And then the HEM model has distinct features. And it's very different principles, if you like, power coming from the spin of the hole. There are flares and sparks. There's Crackle, which will be out. There's six things you can look for, which is narrow of time and whistlers, echoes and polarization. And then there's the caustic crossings in the total flux data, and also in the interferometric visibility. So these are six things you can look for. The data is essentially public, and my radioastronomical colleagues are sort of starting to look for these things and watch the space, see if we find anything. If we find nothing, then probably the MAD models or something like that is right. But it's worth looking for this alternative as well. Apologize for taking a little longer than advertised. Thank you very much indeed.